So in the second half of this, we're going to try to answer those few remaining questions we have about light and where these different colors originate from different elements. So there were a few things that, based on our understanding of light as a wave, that we still couldn't answer, right? The first one being emission of light from a hot object, black body radiation. And I'll show you some pictures of that in a second. The next was the emission of electrons from a metal surface when we shine light on that metal surface. And the last one is the one that I already showed you, the emission of light from electronically excited atoms. So whether we burn that sample, right, and that we're exciting it and it's giving off this color of light, and that color of light is different for each element that we're looking at. So these three things we could not explain by thinking of light as waves. What is black body radiation? Why does shining light on a metal surface cause that surface to conduct electricity? And when I excite a sample, why does it give off light? You're familiar with black body radiation because anytime you turn on the stove and watch that filament on the stove change color and get bright red as it gets hotter and hotter and hotter, that's an example of black body radiation, where as the temperature of an object changes, so does its color. That's kind of interesting to think about. So basically, the hotter it gets, the closer to white that object becomes. And we can see that by looking at the nail over here, right, where that flame is targeted is bright white, bright yellow, and then we see a red and then an orange and then a darker red. The hotter that object becomes, the brighter the light that's released by that object. And so we're familiar with it with these filaments in a stove, but astronomers also use it to tell approximately temperatures of a star for the same reason. The color that's given off by that star is a product of how hot the surface of that star is. And so this work kind of started in the early 1900s, and the first person to kind of look at some of this was Max Planck, he won the Nobel Prize in Physics for this work in 1918. And he was looking at atoms, and he said that atoms oscillated with a definite frequency, nu. And he proposed that there are only certain frequencies available for these vibrations. There are certain only energies available for these vibrations. And he defined that as the energy of those vibrations equals n, where n is a quantum number, times Planck's constant, so basically a constant he derived, times the frequency that that object is vibrating. And so this was kind of a first step in that direction to understanding light, because, okay, these materials, they're vibrating with a frequency, and we can relate that frequency they vibrate to a specific energy level, where n is related to those levels, where n must be any integer, 1, 2, 3, 4, 5, and 6, through infinity. So this was important because instead of thinking of energy as this ramp where we're just gradually increasing in energy, Max Planck quantized energy. He said that energy comes in discrete packets. Discrete packets of energy. So again, going back to that ramp analogy, it's not a linear increase in energy, but it's a stepwise increase in energy, where n, that integer in that we looked at, is related to each of those steps. So I can go up one step, I can go up 2, 3, 4, or I can go down 2 steps, right? Each of those steps is equivalent to a change in energy. So we quantized energy in discrete packets, not this linear increase of walking up a ramp. So Einstein took a look at Planck's work and tried to extend that to light as well. But all that Planck's work was saying was basically, right, if I was a molecule up here on the n equals 3 energy level and I lost energy, right, I would have to lose energy. If I went down from n equals 3 to n equals 2, I would have to lose energy equal to hv. And I could go down that energy level. Or likewise, I could go up 1 or 2 energy levels. So Einstein took a look at that equation and said, how can I apply this to light? So Planck was talking about discrete solids, and he related the energy of the discrete solid to the quantum number n, Planck's constant, times the frequency that that solid vibrated. Well, Einstein looked at that, and this is the pure genius of Einstein. Einstein said, well, light also has a frequency, right? So if light has a frequency, just like solids have a frequency, if I can relate the energy of that solid to the frequency that that solid vibrates, well, then why can't I relate the frequency of that light to the energy of that light? And so as you can see, Einstein's equation is not very far from Planck's equation, right? Einstein came up with, well, the energy of that light must equal Planck's constant times the frequency of that light. And this was revolutionary at the time because now we're associating an energy with that wavelength of light. And he used that to explain the photoelectric effect, and he earned the 1921 Nobel Prize in physics for this work. But it's an incredibly important jump that he took Planck's work that applied to solids and said, if those solids vibrate with a frequency and I can relate that to energy, why can't I relate the energy of light to the frequency of light? An important step in determining the energy associated with light or anything in the electromagnetic spectrum for that matter. And so in putting both of those things we've talked about, right, both of those things we've talked about, the speed of light equals frequency times wavelength, and the energy of that light equals Planck's constant times the frequency, and talking about how these changes occur in discrete regions of energy, right? Now we can start to get a better idea of where these emission spectra are coming from. We look at each of these elements are giving off distinct wavelengths of light. Well, I know all those wavelengths of light have a different frequency, and I can use that frequency associated with that wavelength of light to find an energy. So there must be some kind of energy transition taking place in these atoms that are a discrete energy level, right? They can only go up 1 stair, 2 stairs, 3 stairs. I can't go up 1.5 stairs. But what's important is that each of these wavelengths of light given off, I can now relate it to a frequency and an energy. So there must be some energy transition that's taking place within these atoms, right, that result in this light being released. As we've seen in the previous slide, if we know the wavelength, we can find the frequency because the speed of light is a constant. Once we know the frequency, we can then find the energy of that wavelength of light. It's also possible to combine both of these equations into one to save us from doing 2 calculations when we could just do 1 calculation. So to do that, all I'm going to do is I'm going to solve the first equation for frequency. So if I divide both sides of this equation by wavelength, wavelength cancels out, and I get frequency equals the speed of light over wavelength. I'm going to take that and insert that in the second equation to see that energy equals Planck's constant. So all I'm going to do is replace the frequency with now what frequency equals. Frequency equals the speed of light divided by wavelength. So energy equals Planck's constant times the speed of light divided by wavelength. This is a helpful equation in that it replaces the need to calculate frequency. With this equation, if we have the wavelength of light, we can directly find the energy associated with that wavelength of light because h, Planck's constant, is a constant, and c, the speed of light, is also a constant as well. One other important relationship between these two equations, or within these two equations, I should say, is their relationships. I've already pointed out that frequency and wavelength are inversely related. So as my wavelength increases, my frequency decreases because the product of those two needs to remain constant, needs to equal the speed of light. So that's an inverse relationship between frequency and wavelength. However, with energy, If my frequency increases, Planck's constant, that's not going to change. So if my frequency increases, the energy increases of that wavelength of light. So that's a direct relationship there. Another important distinction when using both of these equations. So here's a sample calculation for you. The phototherapy with blue light of 460 nanometers is used to treat excess bilirubin in newborn infants. What is the energy of 1 photon of that light? So before we can start this calculation, we do have to do one unit conversion. Because c, the speed of light, is given as 3 times 10 to the 8th meters per second. And I have wavelength in nanometers. So I need to convert my wavelength from nanometers into meters. And to do that, I know that for every 1 meter, I have 1 times 10 to the 9th nanometers. So 460 nanometers is 4.6 times 10 to the minus 7 meters. Now I can find the energy of this wavelength of light. So energy equals Planck's constant, 6.626 times 10 to the minus 34 joules times seconds times the speed of light, 3 times 10 to the 8th meters per second, divided by my wavelength of 4.60 times 10 to the minus 7. So let's look at units real quick. When I multiply here, seconds will cancel out, and then when I divide, meters will cancel out, and that's good because I'm looking for energy. Units of energy should be in joules. So when I multiply and divide, I get approximately 4.32 times 10 to the minus 19 joules. So now, using this equation, using the combined equation, we can go directly from wavelength to energy of that light. So the other aspect that this formula helped us figure out and helped us explain was the photoelectric effect. And the photoelectric effect is basically if you shine the correct wavelength of light on a metal surface, right? We're shining this light on a metal surface, you're able to kick electrons out of that metal surface. That is the photoelectric effect. Specific wavelength of light are able to eject electrons from a metal surface. So it's not all wavelengths of light, just specific wavelengths of light, and it changed with the metal as well. So certain wavelengths of light were able to kick electrons out of the metal surface for certain metals. So for example, violet light could cause potassium to lose electrons, whereas red light had no effect on that. So how could we explain that? And now we have the equation of energy equals Planck's constant times frequency. Well, now we know violet light and red light have two different frequencies. We know now that we can relate that frequency to an energy, and now maybe there's an energy component here to causing those electrons, right, to be ejected from the metal surface. Both of those wavelengths of light are different. They both have different energies. Maybe there's an energy variable that we haven't considered before. And that's what Einstein worked on with this equation of energy equals Planck's constant times frequency, that this light must behave like a particle. It must have a certain amount of energy associated with it. And when that single photon of light hits that metal surface, if it has enough energy, if it has the correct amount of energy, it's able to hit that metal surface and kick the electron out of that surface. And then after that photon hits the metal surface, it ceases to exist and it's absorbed by that metal surface. But what we need, right, that specific frequency is associated with a specific energy, and there's an energy requirement to being able to kick an electron out of that metal surface. So this is an important step in understanding the photoelectric effect and applying an energy to light, right? This was the first time it had been done. It was revolutionary to kind of think about that light could behave as both a wave and also a particle at the same time, right? That's very hard to think about something that behaves like both a light wave and a particle that we're associating energy to. And so this is the photoelectric effect. I could take violet light and shine that violet light on the metal surface, and that's capable of ejecting electrons from the metal surface. Because we looked at the electromagnetic spectrum, right, violet light is closer to 400 nanometers of wavelength, so it's a higher energy than red light. Red light's closer to 750 nanometers, so it's a longer wavelength, lower energy. I shine that red light on the metal surface, nothing happens because it does not meet the energy threshold. It does not meet the energy requirement to kick an electron out of this metal surface. One thing to think about here, one thing to understand the difference between is if I just took a single violet light and shined it on this metal surface, that would work. It would kick electrons out of the metal surface. If I took a really, really bright red light or 100 red lights and exposed that to the metal surface, still nothing would happen because in that case, we're comparing intensities, right? Intensity, that's not going to change the energy of that wavelength of light. It's the color of the light that's associated with the wavelength, and that's what's associated with the frequency. So in changing the intensity of light would have no impact on this experiment. And so this setup, right, the wave-particle duality of light, in that we can think about light as a wave. We can use light as a wave to explain most of how we understand and work with light. And we can calculate that frequency and that wavelength, but now we can also take that frequency and relate it to a specific energy as well. And that's very important. And so going back to that previous example where we were talking about the violet light versus the red light, as you can see in this example, right, the violet light around 400 nanometers, right, on this end has a higher frequency and a higher energy, whereas red light on this end, we're talking about a longer wavelength, lower frequency, lower energy. And so really the important things from today's lecture, you should be able to do calculations with both of these equations as well as the combined equation, right? Energy equals Planck's constant times the speed of light divided by my wavelength. And really understand kind of the importance of these experiments, importance of these observations, that those discrete wavelengths of light that are given off by an excited electron, right, there's a reason behind that. And we're going to get to that reason in the next lecture on Tuesday. But those discrete regions in energy, right, they're telling you something about that atom. And it's because they're giving off those discrete wavelengths of light that correspond to discrete energy regions, right, that we can help us understand certain transitions that are taking place within those atoms. So for Monday, we've got to finish Chapter 5 homework, Chapter 4 homework, and then on Monday, we're going to have the midterm exam encompassing Chapters 1 through 5. It'll be an open 24-hour exam. Tuesday's lecture, June 9th, we're going to finish Chapter 6. We're going to finish talking about quantum mechanics. That'll all be in PlayPosit. I will also hold a live lecture on Tuesday to review the exam, just talk about some key points from the exam. So let me know if you've got any questions. I'll have office hours on Thursday. I'll do the review session on Friday. On Blackboard, collaborate from 11 a.m. to 12 p.m., where I'll go over that practice exam.